the simplest quantum system. Simplest quantum system. So in order to decide what could be the simplest quantum system, you could say, well, a particle in a box. It's very simple. But in a sense, it's not all that simple. It has infinitely many states. All these functions on an interval, and then the energy eigenstates, there were infinitely many of them. So not that simple. Okay, so infinite bound states, something with one bound state. Okay, a delta function potential, just one bound state. But it has infinitely many scattering states. It's still complicated. So what is it? What could be simpler? Well, suppose you have the Schrödinger equation, H psi. And we work in general. We know that this thing has energy eigenstates, and probably we should focus on them. So psi equal e to the minus I et over h bar little psi, and then you have h psi equal e psi. So that is quantum mechanics. And you could say, well, you know, it's up to me to decide what the Hamiltonian is if I want to invent the simplest quantum mechanical system. On the other hand, there are some things that should be true. These are complex numbers, energies. H must be an operator that has units of energy. And we also saw that if we want probabilities that are going to be associated with psi squared to be conserved, we need H to be Hermitian. So there should be some notion of inner product, some sort of operation that gives us numbers. We used to go with phi, psi. That gives a number. Belongs to the complex numbers in general. And it has the property that somehow it conjugates this thing, it has this, and integrates. But maybe if you're doing the simplest quantum mechanical system in the world, it will be simpler than an integral. Integrals are complicated. But anyway, we have something like that, and we want H to be Hermitian. So let me write this thing. For any operator A, this is equal to A dagger psi. And that's a Hermitian conjugate. That's a general definition. And we want H to be Hermitian. So H dagger equal H. Okay, so in some sense, you could say that's quantum mechanics for you. It's a Schrödinger equation, a Hamiltonian, an inner product, a notion of Hermitian operators, and then you're supposed to solve it. And what we've done is solve this for a whole semester and try to understand some physics out of it. But we started with the notion that something simple would be a particle living in one dimension. And that's a very reasonable thought, motivated from classical mechanics, that surely we have particles that move, and moving in 3 dimensions is more complicated, so we waited towards the end of the semester to do 3 dimensions. But moving in 1 dimension is already kind of interesting and complicated. So we had psi's of x that represented the fact that the particle could be anywhere here. So how can I simplify this? Well, the key to simplifying this is maybe not to be too attached to the physics for a while and try to visualize what could you describe that was simpler. So suppose the particle could only live at 2 points, x1 and x2. The particle can be here or here. Now we've cut the real line down to just 2 points. It can only be in this point or that point. And you say, well, that's very unphysical. But let's wait a second and think of this. What does that mean? Well, we used to have a psi of x that could be anywhere, and we wrote it as a function. But now that it can, if I think of this, the simplest thing, okay, the simplest thing is a particle is just at 1 point. There's only 1 point. The whole world for the particle is 1 point, and it's there. But that probably is not too interesting, because the particle is there. The probability to find it there is always 1, and what can you do with it? But if you have 2 points, there's room for funny things to happen. So we'll assume that the particle can be in 2 points. So from all of this, psi of x will go to a new psi of x that has 2 pieces of information, the value of psi at x1 and the value of psi at x2. And those are 2 numbers, alpha and beta. Alpha squared would be the probability to be at x1. Beta squared would be the probability to be at x2. And this may remind you already of something we were doing with interferometers, in which the photon could be in the upper branch or the lower branch, and you had 2 numbers. So this is somewhat analogous, except that the interferometer, you could eventually put more beam splitters and have maybe later 3 branches or 4 branches or things like that. Here I want to consider 2 things, a particle there. So one thing that this could be strictly that, but now let's relax our assumptions. It could also mean, for example, that you have a box and a partition, and there's the left side of the box and the right side of the box, and the molecule can either be on the left side or on the right side. That's a fairly physical question. So here you could be probability, the amplitude to be on the left or amplitude to be on the right, a 2-component vector, just like that. One would be the amplitude to be in either one, and maybe that amplitude changes in time. Or it could be that you have a particle, and suddenly you discover that, yeah, the particle is at rest, it's not moving, it's not doing anything, it's at 1 single point, not 2 points, but actually this particle has maybe something called spin, and the spin can be up or the spin can be down. Well, we could invent something, we could call it spin, or a particle could be in this state or in that state. And if that's possible for a particle, you could have here the amplitude for up spin and the amplitude for down spin. And those would be the 2 numbers. So, you know, it's lots of possibilities. In a sense, this is a classic problem waiting for a physical application in quantum mechanics. So let's push it a little more. Now, how would we do inner products? You know, we decided, okay, you need to do inner products. And what was the inner product of two functions, phi and psi? Was the integral dx of phi star of x1 times phi star of x times psi of x. And what you're really doing is taking the values of the first wave function at one point, complex conjugating it, take the value of the second wave function at the same point, complex conjugating it. So if you would have two vectors like this, alpha and beta, the first wave function, alpha 1, beta 1, and the second wave function, alpha 2, beta 2, the inner product, psi 1, psi 2, should be the analog of this thing, which is multiply things at the same point. So you should do the alpha 1 star times alpha 2 plus beta 1 star times beta 2. That would be the nice way to do this. You could think of this as having transposed this, alpha 1, and complex conjugated it, beta 1, and then the matrix product with alpha 1, beta 1. So you transpose complex conjugate the first, and you do that with the second. You know, when you study a little more quantum mechanics in 805, you will explore this analogy even more in that you will think of a wave function as a column vector, infinite one, psi at 0, psi at epsilon, psi at 2 epsilon, psi at minus epsilon. So you've sliced the x-axis and construct an infinite vector. And that's your old wave function. So it's not so unnatural to do this. And this will be our inner product. So how about H being Hermitian? That just means for matrices that H transpose complex conjugated, that's dagger, Hermitian, is equal to H. And you may have seen that that's what dagger means. You transpose and complex conjugate. If you haven't seen it, you could prove it now using this rule for the inner product, because the inner product will tell you how to construct the dagger of any operator. And you will find that indeed the dagger, what it does is transposes and complex conjugates it. And it sort of comes because the inner product transposes and complex conjugates the first object.